So here, the second property, as I mentioned, is the expressive power of a GNN model. How can we investigate or identify the expressiveness of a GNN model? What is expressiveness? How do we actually define it? So the story starts with the K-hop similarity in node local structures. So let's look at the top part together. So first, we have an input graph. Okay, so this is our graph G, and this graph basically what we want to know is the similarity in topology, in local topology or local structure between two nodes. For example, if we look at these two nodes, let's look at node 5 and 4. What do you guys notice? If we look at the degree D, so D here means degree. So the degree of node 5 is actually 2, and the degree of node 4 is 3. So which means these are typologically different. So they have different local structures. One node has 2 connections, and the other node has 3 connections. So they're not similar. They're not identical. So in this case, 5 and 4 have different local topologies. Okay, so here we're looking at one level of neighborhood. So if we're going to take K equals 2, so which means we will look only at K-hop similarity. So K-hop similarity means within a 2-ring neighborhood. Let's identify or find if these two nodes are similar or not here. So from the first layer, from layer, K equals to 1, the first ring, we can see that they are different. So we should stop here and not kind of go deeper, right? So we know that they are different. So next, if we look at a second example, so in this example, we picked 2 nodes. We picked 1 and 3. So 1 has 2 neighbors. It has 2 and 5. And 3 has here, okay, 2 and actually, sorry, there was a typo here. 3 has 4. So let me fix this now. So we're going to fix it quickly. All right. So here we have D2 and 4. All right. Cool. So now in the first layer for K equals 1, we can see that these have the same degree. So the degree of 1 is actually 2, and the degree of 3 is actually 2, right? And then let's look at K, the next ring, okay? So going deeper into the network, so here K equals 2, K-hop. So what is the degree of 2? So the degree of 2 is 4 here, so we have the same nodes, right? And 5 has degree of 2, and 4 has a degree of 3. So although these two have symmetric neighborhoods at this layer, okay, so this is symmetric up to this layer. So if we stop at K equals 1, we can see that these guys are actually, they have symmetric neighborhoods. They have the same kind of, topology for K equals 1. As at K equals 2, as we go deeper, we can see the divergence, right? So here they become divergent because we have 4-2 versus 4-3, which means that in this case, these are actually not, okay, so sorry, let me just take this. So these are actually different. So totally 4 and 3, 1 and 3, they are different at K equals 2. All right, but K equals 1, they're similar. Now, so here we're looking at K equals 2. So let's look at a different example. So the D here, so in this case, we have, I'm going to move this down. So this is K equals 2. All right. So in this case, we have this, sorry guys, so to not mess things up. So we're going to do it. This is K equal. All right. So now for the second, the last graph D, so we're looking at nodes 1 and 5. So 1 has as neighbors 2 and 5, right? 2 and 5. And 5 has 2 and 1, right? So here, what happens is that first 1, what is the degree of 1? It's 2, so we have 2 and 2, so that's fine. They're equal for K equals 1. But for k equals 2, we see a divergence because here 5 has a degree. Actually, these are actually identical. So here I think I made a mistake. This should be this one. Sorry, guys. So it's good that we pick this up now so I can fix the nodes. So here basically, what is the degree of 5? 5 has 2 nodes, right? And then the degree of 1 is actually 2. So they are identical. So here, these are also identical. So I'm going to fix this also. So here we go. Very easy. So these are identical. So in this case, it means that these two have similar neighborhoods. So they are topologically similar, which is a nice thing to at layer 2 at least. Okay. So these two nodes are similar. So they have similar topological topologies up to 2 rings. Okay. Very good. So we have seen different cases. Now, why this is important? Okay. So this is important because if we want to do aggregation, if we want to see if a network, a GNN model can map these neighborhoods, similar neighborhoods similarly, or different neighborhoods in a different way. So it's an important property because you don't want a network to take in similar neighborhoods, like for example here, and map them differently somehow. So you don't want to have the case where similar neighborhood, the same embedding, or the other way around, where you have actually different neighborhoods. Okay, so get same embedding. So you don't want basically nodes 1 and 3 here to be mapped to the same output somehow. So this is something you have. Why? Because node 3 and node 1 have completely different topologies here. So if you do a 2-layer GCN, you should not get exactly the same embedding. If you get the same embedding, it means your network has failed to recognize that these topologies are different. Okay, so you may ask, how can we know? So actually we do aggregation, we do different things, but let's dig deeper one step at a time. So here, the expressive power of a GNN model is defined as follows. So let's look at this step by step. Okay, so an expressive GNN model maximizes its node representation capacity in the embedding space by mapping different local neighborhoods to different embeddings. So this is the most important thing. If the original local neighborhoods are different, we must get different embeddings. Okay, so here this problem is important, particularly when we have identical or similar embeddings. So let's start with the example B here. So if we have this kind of, if we look at the embeddings of node I, so here I kind of transpose the embedding, so I put them horizontally, right? So this is the embedding, right? So here, if I look at this case, what we have different embeddings. We have different embeddings of, for example, the neighbors. We're gonna get different embeddings on top at the root node here, right? So because these are different, if I do a summation, for example, an aggregation, so I sum them up, right? Or I create a mean, for example. It depends on how we do the aggregation. There are different ways, I've seen that. But in any ways, if we take the maximum, the mean, or the summation, you should get 2 different here embeddings. So the embeddings here will be different, even if we have exactly the same topology, right? So the problem arises when we have similar, I would say, identical embeddings. So when you have identical embeddings, what you want to look at is the topology itself. So we don't look at the case where we have different original features. So we start with the case where we assume all our input features are the same. Okay, so they're similar. And in this case, we ask the question, can the network map different local neighborhoods to different embeddings in that we have similar original embeddings, right? So in this case, you can see that, of course, for similar is very, here, if we have three nodes, but so let's say, for example, if I do summation, I have a third node, okay? So I should get these two actually should be different because now, you know, like they come from different topologies, right? But it may be that we need to check which kind of aggregation function we use. Will all aggregation functions give us the same, you know, like a different embeddings if the topology is different? So here, for example, in this example, let's look at this, guys. So let's say we have three identical embeddings, or all of them are identical, okay? So when we do the averaging, if I take average of these three, I'm gonna get exactly the same output. We agree on that. If I take the average as aggregation here for aggregation, I'm get also the same output. So what happens here? What happened here is that we have completely different topologies. We have local neighborhoods, okay? Still, with this average aggregation, my graph mapped, you know, these two nodes onto the same embedding. So it produced the same embedding for this node, okay? Using just this simple aggregation here for this simple naive example. So this is something that we don't want to have. This means that the representation capacity or the expressiveness of this, you know, aggregation function in my network, where I use simple averaging, is not good. So you can see that you find out different problems when you have identical features. So let's have here another scenario, okay? So let's say that I'm gonna give a green vector here. So I'm gonna put a different initialization. So this node will have a green embedding. So now if I do the averaging, you will see that somehow this will be influenced. So now because I have a different embedding here, so these will actually be, you know, different, okay? So in the other case, it was similar, but now they are actually different because I have a different embedding. So you can see when you have different embeddings, the problem doesn't really arise. The problem arises when we do have similar embeddings, right? So so here, let's write it down. So here, the problem arises, this problem of expressiveness, when we have similar embeddings, original embeddings, and we do, for example, aggregation or transformation or any kind of operation, okay? So now moving up next, mathematically, how we define. So this is actually, you know, an injection because you want to map different things onto different things. So mathematically, a highly expressive, let's go back to maybe this. Okay, so a highly expressive GNN model maps local neighborhood into, you know, to node embeddings injectively. So what this means that it uses an injective neighbor aggregation at each layer K. Okay, so our aggregation function needs to be injective. And here, since the neighbor aggregation is modeled through the node computational graph, remember guys, so the aggregation function aggregate neighbors of neighbors of neighbors at particular depth K. We model it through a node computational graph. So we can define we can easily define an expressive GNN as a model that maps nodes with different computation graphs to different embeddings. So now we started looking at computation graphs and see whether, you know, these computation graphs will they map, you know, if they are different, will they allow us to map, you know, the node embeddings if they are identical to completely different embeddings. Okay, so I hope that you guys get this clearly, especially as I said, the problem arises when we have identical original features. So we'll still, will our network still differentiate between different neighborhoods, okay? So now let's look at this together, how we formalize it. So basically, if we have for two nodes N and M. So for two nodes, M and M, which have, okay, so with two let's start here, with two different computational graphs. So if these two nodes have, sorry, so it's not four, if, all right, so we have a typo here. So if two nodes N and M have two different computational graphs, then their embeddings should be different at each layer, okay? So which means if this is the computational graph of node, this is the computational graph. computational graph of nodes n, right? So this is the computational graph of a particular node, for example, right? Here, if they are different, then their embeddings at a particular, each layer k, okay, so we're moving at k, so here we have k plus 1, each layer k and for k plus 1, so we can put it here in general to just make the math consistent for layer k plus 1, then we will have exactly the same embeddings. Okay, we will have, sorry, we said like different embeddings. So this should be actually different, okay? So different computational graphs lead to different embeddings, and this is just a reminder of a particular case that we have seen. So this can be expressed differently. Remember, guys, we can first transform, then aggregate. So there are different ways of doing this. This is a simple update rule that we used before in one of the previous lectures. And you can see that now this should basically be the same. So what is different from between nodes n? What is the term that is dependent on node n? This term, these terms do not depend on n except for actually this one, okay? The embedding of in the previous layer k, and the aggregation, so the neighbors, right? So the aggregation across neighbors, that depends on the matrix A, right? So here, basically, this term is very important. So this term will define, actually, or influence this difference right here. Okay, so that's why in the statement mentioned that an expressive GNN will basically have an injective neighbor aggregation function. All right, cool. So now let's look at the rooted subtree mapping. So as you guys remember, so in terms of aggregations, the aggregations, they happen through the computational graph. And it, you know, like we can call this computational graph also a subtree. In the whole, you know, we have different subtrees that form the forest of computational graphs if we look at each node in our network. So every single node here will have a rooted subtree mapping or a rooted computational graph. And if we aggregate all of them, if you stack all of them, we'll have a forest of, you know, rooted subtrees for computations, okay? For computation of what? Of course, of the embedding that we want to produce, right? So remember what we're doing in GNNs. We're learning these embeddings in a sequential way, in that, you know, we're mapping and embedding onto, you know, like we're learning it recursively throughout the network to get the ultimate compact representation or embedding that will allow us to do classification, regression, or any other task, okay? So forest of rooted subtrees. So now, computational graphs here are identical to rooted subtree structures around each node, which are defined by recursively unfolding neighborhood nodes from the root node. So it's, you know, the unfolding process that we have seen also in the previous lecture. And here, what I want you guys to look at is this case. So let's hypothesize that the node features are identical. So we have different node features. I didn't visualize them here, but you guys can basically think about them this way. So we have many node features. Oops. So here we can put them horizontally if you want. Yeah. So these are the node features. So we have different node features. Okay. So all of them are identical. So what we want to know if the GNN will generate the same embedding for the root nodes. So the goal is to see if we're going to have the same embedding here, yes or no. So you guys can see that for identical embeddings, this statement is true because here you have exactly the same topology or the same subtree, right? Structure exactly the same with the same kind of degree of node distribution across different layers. So layer K, you know, like we have K1 or K equals 1, K equals 2, etc. So as you aggregate, of course, you're going to get similar embeddings if you have similar inputs, similar input embeddings. So these two will map onto the same embedding. So these two root nodes will have similar embeddings because they are similar, right? Now, what happens if they are different? So for example, you can look at, you know, this is the embedding aggregation function from the bottom up to the root node. And you can see for these guys as we go up, so this for this pink node right here, So this pink node has a different subtree graph. So this graph is actually different from these two. So let's call this, graph 1. And so put it somewhere like this is example 1, 2. So 3 is actually different from both. So it should map onto a different embedding. So we should not have similar embeddings. We have basically something like this. It means the graph is not expressive. So it's not good because we have completely different subtrees and we're mapping onto the same thing. So different subtrees should be mapped to different embeddings. And this is what happens here. So we can see that we have a different embedding here for this computational graph at this particular node. All right. So our node is distinguished, from other nodes, thanks to this, nice injective function that we have used in our aggregation. All right. So this is ideal. Now, how can we guarantee this? So, okay, so this has been all formalized. I have reiterated over and over again. What do we want? What do we want? We want all these properties, which are basically saying the same thing in different ways. But how can we actually guarantee this? Okay. So now I want to, move to a more kind of theoretical definition of this problem. And it actually turns out that this is a very ancient problem. So what we want to do, we want to identify is if the topologies of two different graphs are isomorphic or not, are identical or not. Like, do we have the same topology, yes or no, right? So here, the question is, can GNN node embedding distinguish different node embedding neighborhood structure? So yes, if they have been produced using an injective aggregation function at each layer. Okay. Is there a case where GNNs can fail to distinguish different structures? And, here, yes, of course, we can find cases where this fails. And I showed you a case earlier. For example, this case, if we use the mean aggregation here, and we have identical features, if this one was identical, right, it's same, then we're going to get, so with the average, we're going to get similar embedding, which is not good. We don't want to have similar embeddings because the topology is different. We want to have, different embeddings because J has 3 connections, a degree of 3. Node I has a degree of 2. So this is problematic. We have seen already a case where it fails. And previously also, guys, we have seen the case DropGNN. And with the dropout and also the previous lecture, we have seen that when we do one dropout, we remove one random node, right, from these two graphs, we're going to get exactly the same computational graph. So even dropping out a node will make us, will not allow us to distinguish these two different graphs, right? Because they have the same computational output graph when dropping out the node. So some operations such as dropout, right, depends on what we're dropping out, how many nodes, etc. So may not also boost the expressiveness of the network. So dropping out here does not basically drop one, does not enhance the expressiveness. And something nice in this paper that we will see in detail. So basically, the DropGNN paper shows that when we drop multiple nodes simultaneously, when you drop actually paths and a different number of nodes, you can boost this expressiveness. So it's a different way of doing this. This has been published in 2021. And there are different ways of boosting the expressiveness of the network. So one way is kind of, the dropout, but today we're going to focus on the GIN paper, the graph isomorphism network that allows us to kind of nice properties that will guarantee that a network is expressive enough or maximally expressive. Okay, so let's look at this example here. So when does it fail? Another example, Here, so it's a figure from the GNN paper published in 2019. So here I'm going to remove these. So first, we look at, so let's look at all these examples, guys. All right, so we have seen this before. So these examples, first we have mean and max pooling. So if we have the same number of features, here we have 2 different graphs. So you can see that if you're going to take, you know, whether you take the mean or the max, because they have the same identical features, the color here denotes the features, we are not able to distinguish between these 2 topologies. The topologies of V and V prime are different. If you take the average of their, you know, like their embedding, you will get exactly the same average here. So you get exactly the same basically output. And if you take the max also, you apply a max to these 2 embeddings or these 3, at the end, they are identical. So you're going to max them in the same way, right? So basically, mean and max, they both fail in this example, right? So if you aggregate using mean or max, you will not be able to distinguish between these topologies. So now, so let's look at another example. So here, how different aggregators actually compress, you know, information. In the second example, we can see that the average will be different, right? So here, we have another power function. We have different kind of embeddings, right? So in this case, we have, you know, 2 pink embeddings and 1 green. We have 1 green, 1 pink here, right? And what happens is that if you take the max would only look at the maximum value across these 3. So if you're going to add another pink node, it won't change because they are identical. So we're always taking the max. So which means the maximum also fails to distinguish between these two graphs, okay, with different local neighborhoods. So now another example, which is in C. In example B, we have also the mean and the max. So if you take the mean of these 2 nodes, so these 2 make their mean, okay, their average, and you put the average embedding here. And now you have duplicates here. So you have multiplicity of 2, so which means the node is redundant, right? So if you're gonna create the mean of these 4, it will be exactly the same, you know, the same average that we get from this graph. So basically, these 2 have the same average embedding across their neighboring nodes. So we can't differentiate. And the same applies for the maximum, which is very obvious here, okay? So you guys can see that a node with 2 neighbors, a node with 4 neighbors using mean and max kind of, you know, aggregation-based or pooling methods, it doesn't allow us to kind of differentiate topologies. So it turns out that this problem of expressiveness is not as easy as it seems, okay? So we need kind of, we need to define more sophisticated ways and more kind of robust ways of you know, formalizing injective aggregation functions and maybe trying to find a new solution to the problem, okay? So now we're going to look at this. So it turns out that this problem is actually not new. So here, there is the almost of, you know, comparing topologies of 2 different, you know, like graphs, right? Identifying if they're isomorphic or not. It's a very ancient problem that dates back to the 1960s. So here, for example, we have the WL test has been introduced in 1968. So let's look at this together. So first, let's start with the definition of a graph isomorphism. So graph isomorphism asks whether 2 graphs are topologically identical or not. Okay, so if they're topologically identical, it means they are isomorphic. So this is actually a very challenging problem, and there is no polynomial time algorithm that solves it. Now, the WL test of graph isomorphism is a good kind of, you know, like as effective, let's say, solution, computationally quite efficient test, okay, that allows us to distinguish a broad class of graphs already. So it allows us to identify or recognize if there is an isomorphism between pairs of graphs and cover a lot of types of graphs already. Okay, so it may not solve it for a particular subset, but for the majority of graphs, for a large number of graphs, we are able to know if two topologies are isomorphic or not. Okay, so remember, this is important because if we can answer this, if we know that two graphs are isomorphic, we know that their subtrees, are, have a similar topology. So they should not be, they should, the other way around. I think it's the reasoning the other way around is better. So if two graphs are non-isomorphic, they should have different embeddings. Okay, so our goal using this test, we can formalize in this way. So we want, based on this test, historical test, we can say that we want to develop, our goal is to develop a simple architecture that is provably the most expressive amongst a class of GNNs, and that is as powerful as the WL, a graph isomorphism test. Okay, so if we have, an architecture that allows us to distinguish between topologies as good or as powerful as the WL test, isomorphism test, then we can say that our graph is actually expressive because it can aggregate these different topologies differently. Okay, so this is something really important. And here, let me give you a very quick overview of this, WL color refinement test. And basically, the idea is actually very simple, and it is very analogous to the node aggregation GNNs. So the node aggregation GNNs can be also viewed as a coloring algorithm. It has a lot of similarities with WL. So here, first, what we do, we assign an initial color C0 of V to each node V. So the initial color here is 1. So we start with 1. So this is our first color. We have two graphs here. This is graph A, and we have graph B. Okay, so we agree that these graphs here, they at least look different. Our goal is to answer, are these graphs isomorphic? So are they isomorphic? Which means, do they have similar topologies? Regardless of the node indexing, okay, of course. So now the first thing, we assign initial color in the WL color refinement algorithm. So this is the test that we're doing. The second step is basically to iteratively refine the node color by using a hashing function. So the color of node B is updated using basically the color, its color in the previous iteration, and also the color of its an aggregation of the color of its neighbors. So the hash function here, it maps different inputs to different colors. So let's look at this example. Actually, algorithmically, it's so simple. So what we do first, we have our first node. So this is, I'm going to put the root node here. So 1. So these are our first, this is the first color or index that we have for all these guys. So, all right, so 1, 1, 1. And then what we're going to look at is the neighbor. So we're going to add the indices of all neighbors. So this first node has 3 neighbors, has 1 and 1 and 1. So we're going to put 1, 1, 1 here. If we look at this node, it has actually 4 neighbors. So 1, 2, 3, 4. So you guys can see how we do that. This one has only 1 neighbor, which is this guy, right? So you can see it's so simple. Now what happens after we complete the generation of these two graphs? So in the next iteration, now we aggregated the, we put all the neighbors, we stack them. Now we do the hashing. So we need to define a hashing function that maps different numbers into different things. So these are different numbers here. So each, kind of node should be mapped to a particular value depending on what's inside of it, okay? So the next step is basically to define this hashing. So here we have, for example, we can do the summation simply. So this will give us, if we add all these numbers inside this node, we'll get a 4. Here we get 3, right? So 3. So let's move, another 4, 2, 2, etc. So we're going to get these two graphs. So now, and we need to define the hash table. It is injective, which means it maps different inputs to different outputs. So 1 will be indexed as 2, this becomes 3, etc. And these will define different colors. Okay, so 1, 2, 3, 4 actually colors, but it's so nice to see them in numbers because it's easier to track. Okay, now what happens if we reiterate this? So we do this again. So after k steps of color refinement, CKV summarizes the structure of k-hop neighborhood. So basically, after multiple steps, we will see, for example, here that we're gonna get, you know, like different graphs. So at a particular layer, we may get, if we stop here, by the way, guys, if we stop right here, the first k equals 1, then we can say these are at k1, they are isomorphic, they are similar, right? They are similar at k1, isomorphic at k1. But as we go deeper into the network, as we increase the depth and the number of layers, right, we can see that there is a divergence that happens here. So the indexing, the coloring is very different. So these are now different, okay? So in this case, we say that these are non-isomorphic at this level, at this depth, or we can call it layer, also level. So this is a simple example, but you guys can play with this, and this is the key idea. So all you need to understand is just the key principle idea of this WL color refinement algorithm. So now basically what we have completed is the WL test. So how does this work? So these are the different iterative steps of the algorithm. Now I just remind you guys that we wanted to design a graph neural network that has an aggregation function that basically somehow implements this WL test that allows us to identify if two neighborhoods are isomorphic or not inherently. All right. So if a GNN model is as powerful as a WL graph isomorphism test, then it means that it is highly expressive, which means also its aggregation is injective. All right. So all of these elements are connected with each other. Now, the last part here, I would like to give an overview of a very nice paper that tackled this problem. And this paper is called How Powerful Are Graph Neural Networks?